Okay, let's dive right into this explainer. Today, we are going to demystify a foundational academic paper from 1996 that, quite literally, secretly powers the modern internet. If you work with large-scale data at all, you are actively relying on the concepts introduced by Patrick O'Neill, Edward O'Neill, and Gerhard Wykeham. We're going to unpack exactly how their log-structured merge tree, or LSM-Tree, completely redefined the way we design storage engines. Here's our roadmap for today. First, the random write bottleneck. Second, the two-component model. Third, the rolling merge magic. Fourth, scaling up the system. And finally, number 5, the LSM-Tree legacy. Let's get into it. Starting with Section 1, the random write bottleneck. To really appreciate this software, you have to deeply respect the agonizing physical constraints of the hardware it originally ran on, 10 milliseconds. Now, I know that sounds fast, but in computing terms, that is a painfully slow eternity for a single random disk seek. Because physical read and write heads had to mechanically move to the correct track and then wait for the platter to rotate, early databases were capped at a measly 100 random write operations per second. So if you were dealing with write-heavy workloads like log ingestion or telemetry data, that disk head spent all its time just seeking, which created a massive system-choking write bottleneck. So, the crucial takeaway here is the contrast between the dominant tech of the time and this new proposed solution. Traditional B trees updated data in place. That meant if you updated a record, the database had to go find that specific page on the disk and overwrite it, causing this scattered, jumping around chaos. The LSM-Tree proposed a radical alternative. What if we convert those random write seeks into high-speed sequential disk transfers using an append-only model? Think about how this actually operates physically. With the traditional B tree, multiple writes are forced out to completely different scattered disk blocks. It's basically a mechanical nightmare for the disk head. But the LSM tree, it operates more like a continuous linear tape. Writes are just appended sequentially, one write after another, in a single forward pass. Zero seeking. And that means you get incredibly high throughput. Moving right along to Section 2, the two-component model. Now that we clearly see the goal, sequential writing without losing our sort order, let's break down the radical architecture that actually made it possible. Rather than maintaining one giant clunky index on the disk, the 1996 paper brilliantly split the database into two cooperative parts. First, we have C0, which is a volatile memory buffer sitting right in RAM. This component instantly absorbs incoming inserts, updates, and deletes in nanoseconds, purely because RAM has zero physical seek penalty. Then we have C1, which is the durable, read-optimized home down on the persistent disk. So you have your write requests coming in, and they drop straight into that volatile memory, the C0 component, where they're maintained as a dynamic, sorted index. Meanwhile, the C1 component sits out on the persistent disk, laid out perfectly sequentially. The real magic, though, happens in the middle, through a rolling merge process that seamlessly streams that data from RAM down to the disk. Which brings us to Section 3, the rolling merge magic. But here's the massive operational puzzle. RAM is finite, right? You can't just keep absorbing data in memory forever. So if your database grows to gigabytes or even terabytes, how on earth do we merge the small in-memory tree with a massive on-disk tree without loading everything into memory and totally crashing our limited system? This is the absolute aha moment of the whole concept. Are you ready for this? It amazingly only takes about 128 kilobytes of RAM to merge infinitely large files. Because both the memory component and the disk components are already pre-sorted, the system literally never needs to load the entire dataset at once. The engine pulls off this magic trick using a streaming external merge sort. It simply opens a sorted iterator over C0 and a buffered reader over C1, loading just tiny 64 kilobyte chunks at a time. The engine compares the keys at the head of both streams, takes the smaller key, writes it to a new temporary file on disk using a tiny memory buffer, and then just flushes them sequentially. Imagine these background pointers seamlessly scanning through C0 and C1. They operate strictly on the heads of these pre-sorted streams. The merge engine processes them, tosses out stale duplicates, handles deletions, and outputs a brand new, perfectly sorted C1 component at the bottom in a single continuous sweep. The disk head just glides continuously, operating at absolute maximum physical bandwidth. It's so elegant. All right, Section 4, scaling up the system. Of course, out in the real world, as data volumes inevitably explode, a simple two-component system is going to hit a wall. Think about it. If you have a tiny 10 megabyte C0 and a giant 100 gigabyte C1, every single merge forces you to rewrite 100 gigabytes just to save 10 megabytes of new data. That's terribly inefficient. The solution? Cascading merges through intermediate tiers. C0 merges into a 100 megabyte C1, which later merges into a 1 gigabyte C2, and so on. By keeping the size ratio small between tiers, typically a factor of 10, the system drastically reduces write amplification. Now you might be wondering, how do we actually read data back out of this complex cascading system? Well, let's look at how it handles a simple query. The engine searches volatile RAM first. If the key isn't there, then it proceeds to check the durable C1 index down on the disk. If we trace the exact lifecycle of a read request, the read thread goes straight to the mem table, the C0 RAM component, first. Since all new writes go to RAM immediately, searching C0 first naturally guarantees we always find the absolute most up-to-date data. If it returns a not found, the system then drops down to check the disk. Interestingly enough, the original 1996 paper didn't even use complex sequence IDs or multi-version concurrency control. It relied entirely on this physical location hierarchy to ensure consistency. Finally, Section 5, the LSM-Tree legacy. Let's fast forward a bit and examine the enduring legacy of this single academic paper. It's absolutely incredible to trace how the C0 and C1 model directly evolved into the mem tables and S tables powering modern tech giants right now. In 2006, Google Bigtable adopted the concept for distributed scale. Then in 2011, Google dropped LevelDB, which refined the multi-component model into structured leveled compaction. Meta followed that up in 2013 with the highly concurrent RocksDB. And in 2016, Whiskey introduced key-value separation to optimize the whole thing for modern SSDs. It's an unbroken lineage and a huge testament to how a brilliant academic algorithmic optimization triumphed over the physical bottlenecks of storage hardware. Every single one of these modern engines shares the exact same DNA. Even as we have evolved from those clunky mechanical hard drives to blazing fast NVMe flash drives, the core principle of prioritizing sequential I/O remains just as critical today as it was nearly 3 decades ago. So I'll leave you with this final thought-a-pounder. Isn't it fascinating that the spinning mechanical limitations of a 1996 hard drive still dictate the invisible architecture of your data today? Every time you send a message, log a metric, or save a file, you are riding the sequential waves of the log-structured merge tree. Thank you for joining me for this explainer, and keep questioning the foundations of the tech you use every day.